Hello, good morning. Benvindo. This is Ahu Pari from University of Manchester, and I'm a research fellow and a group leader at the Department of Materials. And my research group is based at the Sustainable Materials Innovation Hub in the new Royce building in Manchester. Today, I will talk about designing functional materials using polysaccharide building blocks. But before I start, I'd like to say many thanks to the organizers for their kind invitation. I'm a bit sad that I'm not able to give this talk in person, but I really appreciate the opportunity to showcase my research groups and new activities at Manchester. So in Manchester, my group is looking into a plethora of functionalities in nature. We find a lot of inspiration there. There's a great number of interactions taking place in nature, from molecular interactions like bioluminescence, photoabsorption, and photosynthetic interactions. And when you go to a higher scale, in the few hundred nanometers scales, we see structural coloration is taking place. And when we go to again, similar interaction interfaces at the surfaces from a couple of hundred to few microns. We see a lot of surface interactions within microfluidics, as well as some mechanical actuation mechanisms, as well as activities happening in that space. So this gives us a really interesting point of view in terms of how nature builds up functionality by using very simple chemistries. Because if we look at the common natural building blocks of the nature, we see that most abundant materials, non-toxic materials, are coming together, and they are also using very simple chemical bonding strategies to build up a lot of complex materials. So these materials are also multifunctional, and they are resilient, adaptive, non-toxic, and very sustainable. But apart from that, the complexity comes from a certain structural formation, which is shapes and patterns determine their functionality. And nature likes to make certain geometries actually over and over again. We see that as a repetitive thing. For example, if you look at the basic sugars, more complex sugars, or proteins like silk or collagens, we see that fibrillar formation is very much favored by nature. So that gives us a really good clue where should we be looking for, or what kind of strategies we should be applying for bringing functionalities into place. So for us, we work with cellulose a lot, but we also work with chitin as well. And when you look at the structure of cellulose, we see that there is this fibrillar component which is coming together. Polymers are coming together to make fibers, but these fibers are not all the way through organized. They have very organized crystalline parts as well as amorphous parts to balance between strength of the material as well as the flexibility. So the mechanical strength is optimized this way. So depending on what kind of application we are looking for, we are processing cellulose or chitin in a different way. We can go for nanofibrillation, so we isolate the material itself from its natural state, then fibrillate it to nanofibrils and take the best parts to make composite materials. But we are also looking into breaking down the structures to building blocks. What we call is the colloidal particles. So what we do is we use acid hydrolysis by using sulfuric acid, and we break it down to rod-like particles with surface charges around them. So these are quite stable particles that can form a stable suspension for quite some time. They have a good shelf life, and These suspensions are they can be forming films. They have film forming properties upon evaporation. And the nice thing about is that during the evaporation, rather than forming a polymeric film, the individual particles go through this process we call self-assembly. And the self-assembly takes place spontaneously at room temperature. We don't need to input any energy into it. And upon evaporation, we end up with a colorful film that is made up of a cholesteric phase. The reason for that is because we have rod-like particles, and rod-like particles, when you have a very dilute suspension, we accept it as it is in an isotropic phase. But there are so many stages of the self-assembly, and this is also like other things in biology and in nature. It looks like a very simple, but there is a lot of complexity built into it, because we define the stages of the self-assembly, but at the same time, these stages of the self-assembly are not isolated as we think so. So we assume that we start from an isotropic phase. We have the rod-like particles, and the phase transition boundaries are very closely linked to the aspect ratio of the particles. This is what we also discovered during our modeling studies as well. But even in the isotropic phase, we know that agglomerations are taking place, because when you have two high aspect ratio particles, they like to, and when they are in close proximity, because every now and again they come to that close proximity, they are bundling up. And in the first stage of critical volume concentration, which is again determined by their aspect ratio, we assume that there is this precursors of the crystal nucleation, if you will, are taking place. So that's the tactoids that are bundled up nematic faces that are twisted already. So that's quite a big jump from the completely isotropic phase to tactoids, actually. So we think that even though there is tactoids are forming, the major event happening around this phase is bundling up, forming planes, and some of the little agglomerates of the particles are present, as well as the first stages of the tactoids formation. As the evaporation progresses, we have a more condensed suspension where there's more interactions are taking place. What's happening is that you have the tactoids are starting to merging with each other. They are also the planes of the nematic faces are sedimenting at the bottom of the solid interactions. So the solid interaction, because we are casting a film on a solid substrate, if you remember, so that also is regulating what's happening in this Petri dish. So the final stage, when you have enough agglomeration of the particles, what happens is that there's a gel-like phase transformation, and at this stage not much can happen. Maybe the merger of the tactoids can go further, but no more organization of the material. If they are sitting on an angle at the corner of the film, they are going to stay there. They're not going to move to another phase of the film, basically, and that's why we call it kinetic arrest. And at this kinetic arrest, what happens is that the structure is completely compressed, and it comes into the dry film with cholesteric domains. Luckily, that compressed state is really on the order of the visible wavelength, so we end up with very colorful photonic cellulosic films, basically. So this event and the films you make with through this is very similar to the structural color happens in nature through cellulose polymers of the cellulose themselves. My colleague Silvia Violini, who will be talking later this week, she will also expand on this idea of how cellulose photonics is taking place in nature, as well as you can do it artificially in the labs as well. What we've been studying and understanding the mechanisms that I showed earlier is to make an effort to make highly homogeneous films that you can see here, that almost completely blue films. What was very striking to us at then, when I started this work with Sylvia, was the coloration in the cellulose films was quite digital, which makes sense if you think about these thin films. When you have when you define the pitch, when you can calculate the pitch, it forms into the cholesteric equation nicely, and it gives that the wavelength you expect from. As you go higher in the thicker films, the merger of the tactoids, the formation of the cholesteric layers is getting a little bit messier, or more disorganization, more effects, and more multi-domains are forming, and it is hard to predict from the pitch what is the reflection color of the film overall, because you have so many more domains. But when you have less domains and less defects in the films, the color is quite digitized, which was very nice to see at that time. So from then, that idea onwards, we also showed quite a few applications and functionalities of these films using just the color as a function. One of the ideas was to trap the cholesteric phase into, encapsulated between two layers, flexible layers. And when you compress this by putting a stress onto these cholesteric layers, you're compressing the cholesteric order. So you're shifting the color from red to blue. And we see that this transition from the red to blue is quite linearly related to how much stress you applied. I must come clean. This is not a CNC-based system. This is actually made of hydroxypropyl cellulose, which is a cellulose derivative, and a liquid crystalline phase based on a polymeric phase transformation. I will tell a little bit about this system later. But we were also able to sandwich the cellulose nanocrystals between the shape memory polymers. The polymers we used for that was dodecandiol co-citrate layers. So you make the polymer shape memory polymers and then put the cellulose nanocrystal films in between. And when you change the shape, when you fold it, the color also shifts as well. So this was also very nice to show. And edible colorimetric sensors we developed was, we again work with the HPC for that and encapsulated into shellac. The shellac is a semi-permeable polymer, which allowed us to time the evaporation rate of the HPC liquid crystalline form, and you can time that by by tuning the shellac layer that covers the HPC. So by regulating that, you're also able to regulate the color shift, which can be coupled to any physical event, basically. So that becomes it can be a chemical or a physical timer, essentially. So since that works took place, I made the transition to be an independent group leader in Manchester, and we've been still working on these polymers and ideas, the cellulose as nanocrystals as building blocks themselves. So we are looking into a lot of aspects in these systems, because although we discovered a lot, there's still much more to understand, to connect the optical properties to microstructure, to understand the self-assembly in terms of particle size distribution and the stability of these suspensions, again into optical properties, and to modulate their angular response. We are really aiming to, because because as you see in the wavelength equation, these systems are quite angle dependent, which we are also aiming to make sensors. And to be able to do that, we also want uniform coloration as well as the angle independent coloration as well. And we started playing with their chemistry a little bit, which I'm going to tell just a little bit about as well. And we are running some computational studies to understand how the stages of the self-assembly as well. So by doing that, we are aiming to build functional materials by mostly focusing on the organic hybrids. So most of the materials we are using are aiming to improve the flexibility of these films, because if you look at the cellulose nanocrystals, they are crystalline material, they are quite brittle. So by incorporating alginate silk, hydroxypropyl cellulose, santan, we are able to modulate the flexibility of these films and improve the mechanical strength. We are also looking into bringing more functionality, so we are coupling the system with polypyrrole, NIPAM, polymethyl acrylic acids, and reflectance kind of functional polymers and proteins as well. In terms of material processing, we are also looking into making thin films, as I showed you, but we are doing also 3D, 4D printing, as well as looking into bulk fiber production as well. So one of the things that I want to talk about is filmmaking process and a little bit more insight into the filmmaking as well. I think because of my pointer, this video is not going to work. So yeah. Now it works. So this is a cellulose nanocrystal film that is cast as a square, and this is the usual story, okay? When you cast a film from cellulose nanocrystals, you usually end up with a uniform region in the middle, and you have quite a bit messy part around the edges, which we call coffee ring. And the reason for the coffee ring, and even within the coffee ring, we see that there's a lot of compression zones taking place. So what is happening in the this droplet kind of film formation is this: when you start with a droplet kind of shape, and what happens is that the evaporation rate at the top of the film and at the edges of the film are quite different from each other. And that creates a flux. And the flux pushes the particles towards the edge. So that would be a good storyline, but the story doesn't even stop there. So because of that, you have difference between concentrations here and at the top, or in the middle of the droplet. So that creates another flow that we call Marangoni flow, and that pushes the particles back towards the surface to modulate or to even out the concentration gradient throughout the droplet. So that causes a big difference between the edges of the film as well as the middle of the film. And there is a lot of transition zone between as well. So if you're trying to make uniform films, this is causing a lot of trouble. So we started thinking about how we can modulate this. So the idea came around, we want to different shape of the substrate we are using, because as earlier I said, there's somewhat a lot of influence coming from what kind of substrate you're using, because the substrate dictates how much particle is how much particle is accumulating on the surface and the gelation of the system as well. So we used convex and concave systems to be able to see if we are able to suppress or highlight the coffee ring formation. So when you have a flat film, you have uniform and coffee ring region, and look at the dark field image, it looks very nice and blue in the middle. And when you look at the coffee ring region, we see a red shift at the coffee ring. Well, it is gradually shifting anyways, so it is almost like rainbow colors, everything you can see there. And even in the uniform region, we see different textures and tilting of the angles as well. But when we look at the microstructure, we see the middle of the film is quite regular. And it shows up, it gives us very uniform pitch that is close to blue everywhere. But when we look at the edges of the film, we see this compression is taking place, and we also see the formation of this area is giving us an axis of symmetry and folding of the chiral layers, basically. So we call it chiral fold, but by no means we are thinking of the left turns to right. It is the left folds onto itself, basically. But it also follows the flow diagram of what do you expect from these films as well. So looking at the flat film, concave and convex, in the convex, obviously we are able to push the particles more, but it suppresses the Marangoni flow as well. That's why you all have less of a coffee ring region. And in the concave, we are actually highlighting the Marangoni flow, therefore more accumulation takes place towards the centers, so the coffee ring dominates the whole film formation. And the uniform area of fraction is quite linear, depending on the curvature of the surface, which we are very happy about. And also, we are looking at the relative contact angle versus time, and when we observe how these films are forming and how the pin contact line and the angle is changing, we've seen a lot of things are happening. So it is not very linear. We are able to see that the edges dry much more quickly. There's still a lot of gel state in the middle as well. And at this stage, actually, we see the lifting of the sides of the film as well. We also seen that with the curvature, we are also affecting the evaporation curve as well, which is also nice to see, because this is something that we should bear in mind in terms of slow evaporation or fast evaporation eventually affects the pitch you're getting, because the slower the evaporation rate is, the bluer the films are getting. That's what we observed. That was also an interesting find that is correlated with the coffee ring formation as well. As I said, what we were mostly pleased was what do you model as a Marangoni flow is highly reflected on the formation of the these folding of the chiral folding that I talked about. So this forms a line of symmetry as well as folding of the layers itself. And another thing that we also observed here is that the more we increase the suspension concentration to begin with, that there's also a correlation on how much folding we are getting as well. So that's a storyline that we just submitted, and another storyline that we are working on the submission is modulating the angular dependence of the coloration. That's what we are interested now. The reason for that is two things. When we are asking for making linear films for the uniform coloration all around, that happens because of when you have tilted domains, like when you have linear domains, upon compression, you don't change anything in terms of the wave equation here. But when you have tilted domains, because of the compression, the final contribution from that angle of the pitch is going to be much higher, which is undesired, and this also causes contamination in terms of the completely left-handed circular polarization is not valid anymore, because if you have highly tilted domain, you will have more left and right circular polarization. So we want to address the two. We want uniform layers, but we want those uniform layers to not to have so much angular dependence as well, which is a hard ask if you're if you also work on the optical materials. So to address that, we started working on this gelation idea. So we put another polysaccharide into systems, and xanthan gums is microbial polysaccharide from Xanthomonas campestris, and it is produced by fermentation upon and upon thermal annealing. Xanthan can go through gelation process spontaneously itself as well. And with very small amounts of xanthan, you're able to produce quite viscous gels, actually. A nice thing about this viscous gel is it has a very good shear thinning behavior, actually. So this high shear thinning means it flows very easily, even though it has very high viscosity. So they can provide long-term stability to colloidal systems, which is very interesting for us because we are working with colloidal polysaccharide colloidal systems. Oh, shall we put another polysaccharide into this system that is a colloidal stabilizer? So we still have the similar phases, but we think that we are developing a gel network that causes encapsulation of the tactoids themselves, or the several pitches, maybe few tactoids altogether merge themselves. Kinetic arrest and compression still happens, but it is encapsulated and compartmentalized, and we have more cellular appearance of the films overall. And one more thing that I want you to pay attention is the roughness of these films. So while this is all compartmentalizing the system, it is also the compartments themselves are rough. So we still have this, the CNC films, as you can see, large domains, and a surprising finding is very uniform looking films. It is not as iridescent as before because the xanthan itself doesn't form photonic phases. It is going in between the photonic structures. So the discontinuity and the thin layers between these compartmentalized units is giving us scattering, but it has still very good color response. And another thing we discovered is because xanthan and cellulose, similar polysaccharides, they are sensitive to temperature and humidity. So we are able to do reversible changes in the structure by changing the temperature and humidity of the area as well. As I said, the striking part was the cellulose nanocrystals are forming quite regulated areas of organization, and in between we see the xanthan is forming a heterogeneous phase in between, which we are able to see in the dark field microscopy as well. What we were very pleased about is before we add the xanthan, we have high angular dependency in these films, which reduces with xanthan addition, but also we lose a little bit of the reflection as well. And what is the most surprising for us is xanthan films are actually quite messy. The whole idea of the merger of the cellulose, the tactoids, and then forming this non-uniform films, or we are trying to get this. But we are seeing that although we have so regular coloration, the whole microstructure is not matching to that. So the interplay between order and disorder and scattering and the Bragg interaction is somewhat giving us a uniformity in the color appearance of the films, which is probably regulated by the wrinkled surface, as well as the layers are must be quite regular as well. So that's another storyline. We just finished, and the last two examples, one of them is coming from the cellulose nanocrystals combined with another protein this time. It is coming from reflectance, so we know that cephalopods can change color as a response to their environment, and it comes from this reflectin proteins that forms photonic structures that can swell or contract with ionic interactions, and the ionic interaction is regulated by the central nervous system of the cephalopod itself. So what we have done is we isolated this protein, and we produced it by recombining with the E. coli genes. So we made the recombinant proteins, and we studied their optical properties by making multi-layered films. And they are forming quite strikingly colored films themselves. But as a second stage, we combine them as a layer by layer, alternating layers of reflectin plus cellulose nanocrystals. So the results were even more striking, as you can see, like an Andy Warhol art piece. The modulation of the coloration based on the concentration of the cellulose nanocrystals and how much reflectin we build up on it, and reflecting acting as an amplifier for the color response was quite is a quite nice story, because we never get this much reflection from cellulose nanocrystals before, and these films are quite thin. I must say they are on the order of 3 microns overall. So to get that much reflection from a very thin film is actually quite surprising, but also it's a very interesting find. We are trying to we are thinking the synergy between the protein and the polysaccharide works really, really well. What is better, what was really nice to see actually, that these combined films actually have circular polarization, which was never shown by doing spin coating before. So we are also very pleased about that, these results as well. And the last example I wanted to show is functionalizing hydroxypropyl cellulose by using glutaraldehyde and printing these states of the liquid crystalline mesophases of the HPC, and trying to understand the film forming mechanisms and the microstructure of these mesophases during the evaporation from a thin filament. This is a revised phase diagram of the hydroxypropyl cellulose. just hydroxypropyl cellulose itself. We've seen that there's so much IR and UV interactions are taking place. We are showing this for the first time. And we are able to print these structures from liquid crystalline states. And there was a video here. I'm sorry, it is not working, but we see this regular arrays of wrinkles happening that is coming from the formation of the liquid crystalline phase, because these are highly concentrated phases. As you can see, we are working in the range of 65% of solids in this gels, liquid crystalline phase. And because of the small nozzle sizes we are using in 3D printing, there is quite a high shear buildup in these high solid contents. So what is happening is the polymers are stretching, but then relaxing out at once they are printed out from this small nozzles. And this kind of formation and deformation is called Herfrich-Huralt deformation, which is first time showing in the 3D printed liquid crystalline structures. That is quite regulated, and it is all around the circumference of the filaments that we build up actually. We also defined some differences between the skin or the most outer layers and the inner layers of the films as well, which explains now why we are not getting the purely iridescent appearance, but there is some scattering incidents happening there as well. But what we were very interested about was this, we didn't have any angular dependency, and the reason for that reduction of the angular dependency is somewhat similar to morpho butterflies coloration, which actually suppresses the angular dependence by providing this complex wrinkles or pine tree kind of triangular structural formation as well. So as I said, this was a very heavy on the cellulose-based studies, but my group also works with chitins a lot as well. There are some more storylines coming from that area as well. I hope I will be able to share it next year. But starting from these building blocks is very joyful for us, because they allow us to build and design building blocks, play with their chemistry, and then apply to that material processing methods. And we are saying in every step we are able to modulate the material properties, mostly optical properties, but their chemical responsiveness as well, and that can be applied to application and devices. So I leave you here, but I also want to thank my group at Manchester, Luz, Tadeusz, Shashin, Emre, Matt, Yuchan, Hoying, Adrian, Sophia and Jingi for the past few years, for being with me and getting through the pandemic with me. And I also would like to thank the people, the agencies who helped raise money towards our research as well. If you have any further questions, I'm happy to answer via in this live platform, as well as you can get in touch with me. This is my email address. So many thanks, and hope to see you someday in a face-to-face meeting. Thank you so much. Bye.